My name is Hossein Mobasati, and I am going to talk about chapter 12 of my book with Robert. It's about Hodge Locus and some components of the Hodge loci. The definition of Hodge Locus using integral is very simple, and we start with the family of smooth projective varieties, and we take homological cycles. I will introduce the homological version of Hodge Locus, a continuous family of cycles, and then we have to take sections omega 1, omega A of the cohomology bundle, not the whole cohomology bundle, but the part which has to do with this piece of the Hodge filtration, F m half plus 1. Remember that we have used this piece of the Hodge filtration in order to define the notion of a Hodge locus. And so for simplicity, let's take A equal to dimension of this piece. And let's see. So what we do, we integrate all these omega i's over delta t. And the good point is that these functions will be holomorphic functions uh, in a neighborhood of 0 in V. So we have fixed a point or the variety x0, and and since the integrals are depends on t, this we will get these holomorphic functions. And the definition is here. So the analytic hydrolytic passing through 0 and corresponding to the cycle delta, sometimes I write delta equal to delta 0, uh, is the analytic variety, this one. So it is given by the zero set of all these integrals. Just remember that all these integrals to be 0 will imply that delta is a Hodge. This is by definition of a Hodge cycle. So we just consider the definition of a Hodge cycle in families, and instead of when we get a loci in the parameter space. And the another important fact is that we have ideal generated by these holomorphic functions, and actually we want to consider this ideal and not just the analytic variety underlying this ideal. So actually our Hodge locus will be analytic scheme or analytic space, and it is just given by this. So OV delta is just this. So this is, let's say it is V. There is a mistake. And so it is the germ of holomorphic function V divided by this ideal. So this ring might have nilpotent. The ideal might not be reduced, and a lot of bad things which might happen for an ideal might be present in our situation. By the way, I am using two notations for fiber. XT is the same as YT. Anyway, so when in the dimension 2, the Hodge locus is the another Lefschetz locus. But we for the moment we are not interested in the global structure of the Hodge locus. For the global structure of the Hodge locus, we have this theorem by Catani, Delin, and Kaplan. It says that the reducible component of the locus of our, let's say, in the language that I said, of the Hodge locus are algebraic set. Maybe in a simple word I have to say, so we have defined something which is local, and at the end of the day this theorem will imply that in our situation that I already defined, these irreducible component, local irreducible component, are part of a algebraic set. Remember that our parameter space is V, everything is inside V. And so this will be, there will be algebraic set in V, which crosses this point 0. And actually, different local irreducible components might correspond to the same algebraic set. But in this talk, we will not talk about this theorem of Delinkatani-Kaplan, which this theorem originally was proved that it is a consequence of the Hodge conjecture, and they were able to prove it without assuming the Hodge conjecture. So I have to say that our goal is to compute the Zariski tangent space of the Hodge locus. So remember that this was an analytic scheme. So with this tangent space refer to V delta not just as an analytic variety but as an analytic scheme. And in general context, this can be computed with something called infinitesimal variation of Hodge structures, which is one of the chapters in our book. But it turns out that for hypersurfaces, the description is very elementary. And so here I will discuss this. So in the case of hypersurfaces, instead of the notation y v, I have used the notation x the t with the, let's say, xt fibers. And this is going to be the full family of hypersurfaces in the sense that if we take all homogeneous polynomials of degree d, t will be some open subset of this one, parameterizing smooth hypersurfaces. Anyway, so we have to define the Hodge locus inside OT0, and so by Griffith's theorem, we know the part of the Hodge filtration of the hypersurface that we needed for definition of our integrals, and this is exactly by the part what we need. This will form this will generate this f and half plus one piece, and so we will need these functions in order to uh, to uh, to define the Hodge locus. So in this case, the Hodge locus will be just the analytic Hodge locus passing through 0 point will be just a zero set of this one, and then if we have to consider it as a scheme, so the ring of function of our Hodge locus will be OT0 divided by this ideal. So remember from our previous video that attached to a Hodge cycle, we can always construct an Artinian-Gorenstein ideal and Artinian-Gorenstein algebra. And so this is I delta that we have to consider. So in the case of hypersurfaces, it turns out that we can compute the tangent space of the Hodge locus. And if we define the Hodge locus negative as before, then the Zariski tangent space is just this d's, where d is the degree of the hypersurfaces that we have started. And this is actually the thing that we find the before defining this Artinian-Gorenstein ring. So the proof is basically a calculus. So the idea is that if the f depends on a lot of parameters, each monomial in the expression of f has a parameter, and if we make derivation with respect to this t alpha, then we will have we will have this integrate derivation will go inside, and then we will use the classical derivation, and then we will have this equality where this q is derivation of with respect to t alpha, and so this is for p, which it is. So these p's are the ones which comes from the definition of a Hodge locus. We want to compute the linear part of these guys for I less than n half and I n half, because these define the notion of Hodge locus. And it turns out that for in this case, we land on again a differential form which is in fn half plus 1. So by definition of the Hodge cycle or Hodge local, it is 0. And just in the case of I equal n half, that we get an integral which might not be closed. So I n uh, 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 in half. And so the linear part of the corresponding defining equation of the Hodge locus will be this one. So the tangent space is the kernel of this linear part, and this means that we have to put delta 0, this equal to 0. So the kernel will be exactly the one that we defined for I delta. So the next corollary is immediate, because remember that we had proof that GF P delta were constructed by the Poincare duality for delta. This is I delta, and then its D pieces are also the same. So at the end, our tangent space will be this this one. Here, where for the sake of completeness, we have repeated the proof again here. In the next remaining minutes, I will introduce two class of components for Hodge locus. So the first one is very simple. We consider hypersurfaces given by these kind of f's, and this has a lot of complete intersection algebraic cycles. For example, this non-algebraic cycles inside this x. So x is given by f equal to 0, projectivization of this guy inside p n plus 1. And I will, so in the parameter space of degree d hypersurface, I'll denote by t underline d, the space of these polynomials or hypersurface. So d underlines means this collection of all these di's, which are a degree of this f1, f2, fn plus 1. So this is of course an algebraic set, but once again I will consider just as local analytic variety. So the first statement is that let me see the analytic branch of TD corresponding to the formation of X, then the Hodge locus, and this is the Hodge locus, and this is the one that we defined. These are the same. Maybe a few words about this VC, and so this is the point is that when we consider this zero representing x0, and then we consider this analytic algebraic variety t underline t. So this might cross this zero many times, and here we just consider one analytic branch of this guy, and we call it this one we is z. So anyway, this this theorem actually Well, the point is that we can put also a scheme structure here, and something that I skipped is note is strongly alternative Hodge conjecture and so on. That I think I will do another video for this one. But for the moment, just take this identity between two topological space. In particular, I am not using I'm not using the the scheme structure here. Just consider it as equality of sets. So this theorem appears in Dan's article, uh, and without any reason, he puts some extra condition which are not necessary. And I will give a very simplified version of the proof now. So the basic idea is that all these algebraic couplet intersection algebraic cycles, they are equal up to sign and modulo the polarization. This is because, for instance, if you just take f2 equal to 0, f2 equal to 0, fn plus 1 equal to 0, and then these two guys equal to 0. So you will get z1 plus z2 sum, which is a multiplex of the polarization, z infinity. Z1 correspond to the f1, z2 correspond to fn plus 2. And let's take the homology class. And at the end, this is z1 will be minus z2 modulo of polarization. So that's why we have this statement for complex. So at the end, it turns out that this ideal is inside here, and they had both these ideals are Artinian-Goranechtein of the same circle, and with the classical properties of Artinian-Goranechtein ring, we will conclude that there are equality here, and 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 the simple calculation shows that actually this guy here is the tangent space of VZ at the point that we are doing computations. So our next example of a component of Hodge locus is obtained by taking a sum of two linear cycles. So we will take a hypersurface, and that inside this hypersurface we consider two projective space of n dimension and half. They will intersect in each other in Pm, and we will assume that this condition holds. In the proof, it will be clear why this condition pops up in a natural way. So you can consider the Hodge locus corresponding to some of these homology class of these two cycles. Here are check they are any integers not equal to 0, and and here we have considered the intersection of two Hodge locus. So p and half is a complete intersection of type 1, 1, 1, 1, 1, 1. Um, and so by our previous theorem, we have this V p and half is the same as the V Hodge locus, the homology class of p and half. So basically, this guy is the loci of hypersurfaces containing two p and half check intersecting each other in some Pm. So this means that this Hodge locus for this Hodge locus parameterize these two algebraic cycles. The reason why this is state has as a conjecture is that the next results are only for x0, x or x0 Fermat, and our computations are done just around Fermat. So, what is the next results? Okay, so maybe this, let's say, taking Fermat. Fermat has a lot of linear cycles. Let's, in our case, we have taken these linear cycles, which intersect in some Pn. Zeta 2, these are primitive level unity. So we can prove the conjecture 12.3 in this case. So maybe I have to say that the proof basically in this first article, it is based on the computer calculation of the tangent space of the Hodge locus, and later Roberto, in his thesis, was able to give a theoretical proof. And once you go through the proof, you will you will see how this condition pops up in a natural way. So the proof consists of two steps. The theoretical proof, which is basically due to Roberto. First, we have to compute p delta for this delta p and half and p and half check that I showed you. It's explicit. So for this one, we call it p1, and for this one, let's call it p2. And you see that we can get explicit expression for p1 and p2. It's this one, r1q, r2q, and then r1, r2 are given here. So they are polynomial in xi's with 2D roots of unity. And then, so once this is done, then we can forget geometry, and we our the statement that we have to prove is this one. And actually, Roberto was able to prove in a more general identity, and the identity is this one. So this the intersection of these ideals, at the end is the same of this one, and this is only valid in these cases. And for simplicity, I will skip the proof.